everyone. I hope you're full of energy today because we're discussing energy. So we're all excited, and I like this. I say this about every section. I like this section. Energy's fun, okay? So we're going to get lots of energy. Hopefully we're ready for this. So, have you ever thought about how many different types of energy there are? There's lots, but of course we don't deal with all of them because some of them are quite abstract. So we're only going to deal with a couple, but there's lots and lots and lots. And energy is all the same thing essentially. We just are looking at how the energy influences mechanics, how it influences motion. Okay? So, we've done a lot of stuff with motion in one dimension over this series. We've done all of this here, and today we're going to look at energy. What are our keywords? Energy, okay. Kinetic energy, hopefully you've heard about this before. Potential energy. Mechanical energy, now that's a new one. And with those three, so now we need to take energy and we're going to split it apart, okay? So let's look at what we've got. Energy can be divided into a whole bunch of types. We're only going to look at three in particular: kinetic, potential, and mechanical. Okay, mechanical is actually not an energy on its own, it's a total energy, okay? When we've done that, we're going to define each of those energies so we know where we will find them. And then we're going to need to do some calculations. It's how we always do it. We define what we're working with, then we look at how we calculate it, because we want to do calculations. We want to be able to work with it. First one is potential energy. Now, this is an energy that an object possesses due to its position in a gravitational field. So for this section, we're working with gravitational potential energy. There's lots of others. There's electrical potential, there's chemical potential, but we're only working with gravitational potential. So we need to know where the object is in terms of a gravitational field, in other words, on Earth, okay? Our equation is EP equals mgh, where EP stands for potential energy, and we measure that in joules, capital J. M is mass, which we measure in kilograms. G is acceleration due to gravity, which is a constant 9.8 meters per second squared. And H is height. All right, and that is height from a reference point. So we need to know where I'm measuring it from. Then we have kinetic energy, and that's the energy an object possesses because of its movement. So it has to be moving. So my hands, because they move all the time, have lots of kinetic energy. My feet, because they're relatively, well, they are still at the moment, they have no kinetic energy, okay? So we have to have movement. The equation is EK equals a half mv squared, where EK is kinetic energy. Again, it's measured in joules. Half is a half, it's a constant. M is mass, again measured in kilograms. And V is velocity. Sometimes they're going to describe that as speed. It's the motion, it's in meters per second. Now, what I haven't actually said so far is that energy is a scalar. So energy doesn't have a direction. And for our purposes, energy should always be positive. Okay, you can have a negative energy, but that's not a direction. It just means that energy was taken away. But for what we're doing at the moment, we should only have positive energies, okay? You shouldn't get any negatives. Then we have mechanical energy, and this is a total. So mechanical energy is the sum of an object's gravitational potential and its kinetic. It's very specific. It's called mechanical energy because we're looking at the mechanics of motion. So we have to keep in the back of our mind that we're looking at the motion of an object, and how an object will move depends on its velocity, and with potential it depends on its height. So we'll write it like this, okay? EM is mechanical energy measured in joules. EP is potential energy, also measured in joules. And EK is kinetic energy, also measured in joules. All of these are measured in joules, okay? When we look at mechanical energy, it's going to be a total. Now be careful here in that an object doesn't have to have potential and kinetic. It could have maybe just kinetic, or it could have just potential, okay? But mechanical energy means you look at both together, and you need to make a decision as to whether it has both or just one of the two, okay? So, that was our brief introduction. We're going to take a short break, and when we come back, we'll do some investigation. So I'll see you in a couple of minutes. Welcome back. Let's continue looking at energy. Hopefully we've had something to drink, or we've gone and had a quick run around, and we've got lots of energy for this. So, let's investigate kinetic energy. Okay, so here what we're going to do is I've got a little animation. All right, it's all about stopping distance, but we're not worried about this. I just want you to see what happens when the cars move. So, we're going to look at the first car, and so only this top one's going to go. Watch. It runs. We're not worrying about what happens with the other cars, and it's going very, very, very slowly. So because it's going very slowly, it stops quite quickly, so it doesn't have a lot of kinetic energy. Let's reset. So now we're going to have two cars. Now this car's going faster, so now I want you to watch. Okay, it's going to go, then it's got to stop, and oh boy, thanks. But it had more kinetic energy to start off with, so it travels far further because it was faster. Okay, let's go to 3. Oopsie, let's go to 3. Let's see what happens. See, that one's going much faster now. And it goes, keep going, it's going. And there it goes. It stops. Smallest kinetic energy, bigger kinetic energy, even bigger kinetic energy. Okay? Let's see if we now have 4. So we have 4. They're starting a bit further, just so they're going faster. And let's see, they all get there at the same time. And it's going further and further and further and further and further. And eventually it stops. There we go. Okay. The faster it was going, the further it traveled. Okay. So now what we need to do is when we come back here, okay, what I needed you to see with this is that we kept mass constant. Okay? So we kept the same car. But every time we did it, we had the same car was going faster. The faster it went, the further the distance it traveled, okay? So when we look at this, it means that it had more kinetic energy. Mass does affect kinetic energy, but speed is very important. And in fact, the velocity that it's going at is more important in terms of how it changes the kinetic energy than the mass is, okay? Because if we look at the equation, we know that EK equals a half mv squared. The half is a constant. That's not going to change. We're not going to worry about how we got to the half. That doesn't matter. But mass is directly proportional to the kinetic energy. So bigger objects have bigger kinetic energies when they're moving because they've got a bigger mass. Smaller objects will have smaller kinetic energies. That's a direct proportion. If mass doubles, kinetic energy doubles. If mass becomes 3 times smaller, kinetic energy becomes 3 times smaller. That's an easy relationship. Kinetic energy and velocity, this one's a little more complicated because it's v squared. There's also a direct proportion, but kinetic energy is directly proportional to the velocity squared. So if velocity doubles, kinetic energy becomes 4 times bigger because we went 2v, 2 squared is 4. So we've got to keep that in mind, which means for us that a change in velocity has a much bigger effect on kinetic energy than a change in mass does, okay? So these are the relationships we were just talking about. Kinetic energy, directly proportional. Remember, this sign means directly proportional. There we go, to v squared. And it's directly proportional to mass. So the two of them go together, okay? Let's look at potential energy. And again, I've got something to show you, but we're going to do some calculations with it. So I'm going to get that side ready. And here we go. So here we have a scientist who is going to drop a ball from a height. At the moment, it's at 3.6 meters above the ground. I'm not going to worry too much about the time, okay? That's not why we're doing this. we're going to look at the potential. So now I have a tennis ball, which is 59 grams, okay? So I'm going to drop the ball. There we go. So the ball drops, and then it bounces, and it stops at 2 meters, all right? So if we go back here, what we knew was the mass of my tennis ball was 59 grams. Remember, in physics, we can't work in grams. We have to work in kilograms. So I'm going to divide that by 1,000, okay? And just in case, let's just quickly do 59 divided by 1,000. Oopsie, gives me 0.059. So that's the tennis ball. The original height was 3.6 meters, okay? I can work out how much potential energy it has. So I can go potential energy is mass times gravity times height. The mass is 0.059. Gravity is always 9.8. That was 3,6. Absolutely need a calculator now. So we've got 0.059 times 9.8 times 3.6, 2,08 joules. Okay? We then saw that it went back up to a height of 2 meters. So if I now change this height to 2 meters, we now need to say to ourselves, well, will the potential energy change? Height has changed. So what the potential now becomes, mgh, so 0,059, we've got 9,8 times 2 this time. Have to use our calculators. All right, so let's do the calculation, and we get 0.059 times 9,8 times 2, and has to be a decimal, so we've got 1,16, because we're going to do to 2 decimal places. Now, here we can see that I changed the height, so I changed the potential energy, but let's see if we can get something that's a little bit more, whether they're directly proportional or that sort of thing. So we're going to go back to our little man. Okay, there he is. And we're going to reset, and I'm actually going to drop him down. So at the moment he's 3,6. If I take him down to 1,8, so he's going down, it's taking him a while. So what I'm doing is I'm going to halve the distance, at least I hope I can get there. I'm not sure I can, actually. Can he go that far? No. Okay, so let's take him back up to, that'll do. No, let's take him back up. We'll do mass instead, because that'll be easier. So here we go up, he's going up, he's going up, he's going up. Let's stop him at 3.6. Let's use something other than a tennis ball. Hockey ball. 50, we did it 59, now we've got 162. That's about 3 times bigger, okay? Not quite, it's about 2.5. Actually, let's just check how many times bigger it is. So I'm going to take the 162 divided by 59, and it's 2.7. Okay, that's a nice sort of round number. So what we're going to do now is we're going to drop it from the same height as we did the last one. So let's just get rid of that. So now we're going to drop it. And he hits the ground. And interesting, do you see it doesn't actually go as high? That's quite an interesting, that's about energy changes and what happens when it hits the ground, okay? Because the hockey ball is harder, it's heavier, there's a whole bunch of things that happen here that we're not worried about right now. So let's go back to our calculations. And what I'm going to do here is let's get rid of this. I'm now going to do the calculation with the 1,62 grams. So my mass was 162 grams. So that's 0,162, okay? On the calculator, we realized that the difference was 2,75. I'm just going to put that in the corner for us to keep note of, okay? Just putting that there for now. Now we can go EP equals mgh 0,162 times 9,8. The height was 3.6. Let's calculate that quickly. 162, there we go, times 9.8 times 3.6. And we get 5,72. All right, so heavier mass, bigger potential. Now what I'm going to do here is I'm going to take that 5,72, divide by the 2,08, and see if I get 2,75. And then I'll explain to you why I'm doing that. So 5,72 divided by, and it was 2,08, 2,75. What that means for me is that potential energy is directly proportional to the mass. The mass changed by a factor of 2.75, energy changed by a factor of 2.75. So, potential energy is directly proportional to height, and it's directly proportional to mass. If one increases, the other increases. If one decreases, the other decreases, but by the same amount. If height doubles, potential doubles. If mass is 2 times smaller, potential is 2 times smaller. Okay? With mechanical energy, I just need you to remember that mechanical energy is EP plus EK. There's no direct proportionalities here, okay? So I can't say if potential doubles, mechanical energy will double. Why? Because of the plus sign. What I can say to you, though, is if potential energy gets bigger, mechanical energy will get bigger. If kinetic energy gets bigger, potential energy, mechanical will get bigger. But I can't use the word directly proportional, okay? But they are proportional. So in other words, if I increase EP, E mechanical will also increase. But I can't say by the same amount. The same happens if I increase EK, okay? We are going to look later on at the relationship between those two and how mechanical works, how mechanical energy works. But for now, it's just about the fact that they increase together or they decrease together. Welcome back, everyone. Wow, we've discussed potential, we've discussed kinetic. Let's do some calculations, okay, just so we can see how easy this section really is. First question, a crane at a scrapyard lifts a car with a mass of 1,500 kilograms to a height of 10 meters above the ground. Calculate the car's potential energy. We like questions like this, so let's write down what we know. Mass, 1,500 kilograms. We're happy because it's in kilograms. Height is 10 meters, and they want potential energy. We know potential energy is mass times gravity times height. Now here you need to remember, because they're not going to tell you that G is 9,8 meters per second squared. It is on your information sheet, but I'm hoping by the time you write tests and exams on this, you've worked with it so much that it's a value that's ingrained in your head. But if it's not, look it up, okay? So, 1,500 times 9,8 times 10. Now, we definitely can't do this in our head. So 1,500 times 9.8 times 10. Wow, 147,000 joules. It's a big number. I'm okay with that number. Whenever I get to an answer, I need to say to myself, does my answer make sense? I've got a car of mass 1,500 kilograms. It is very heavy. And 10 meters is actually quite high. So I'm going, it's high and it's heavy. I'm okay with that answer. So I'm not concerned. Next question. A crate of 250 kilograms is lifted to a height of 2.5 meters. Now here I've got a smaller height and a smaller mass. I'm going to expect a smaller answer than what I just had. Let's see if that's what happens. Mass, 250 kilograms. Height, 2.5. So, potential energy is mass times gravity times height. So 250 times 9.8, because that's a constant, times 2.5, and we go 250 times 9.8 times 2.5, 6,125. 6,125 joules. I was about to put meters. Joules. I'm happy with that. Again, it's quite a big number, but 250 kilograms is quite heavy. 2.5 meters, not as high, so I didn't expect as big a number as I got in the last one. Okay? A ball, ooh, now they're changing things up a little bit. Now they tell you a ball has a potential energy of 300 joules at a height of 2.5, and I want the mass. Now, look at that value. 300 joules is small. I'm expecting a small mass. Okay, so even before I start the question, I'm thinking about the information that's been given to me. So, they tell us potential is 300, height is 2.5, and they want m. So we start where we always start. Equation, potential equals mgh. Potential is 300. We don't know mass. G is 9.8. Height is 2.5. We want m on its own. So we're going to go 300 divided by 9.8 times 2.5. Definitely need calculators for this one. So 300 divided by 9.8 times 2.5, and look there, 12.24. Okay, so we're getting 12.24 grams. Not grams, kilograms. That's still quite heavy for a ball, but I'm okay with that. There's nothing wrong with our maths. It's a heavy ball. It would be like an exercise medicine ball maybe. I don't know. We just go with it. A dynamics trolley. Guys, all a dynamics trolley is, it's a wooden block that has wheels on it that we use in a physics lab. Don't stress if you don't know what it is, okay? That's not important. What's important is that they tell you it has a mass of 500 grams. We measure its speed at 4 meters per second. Now, some of you are going to be going, but wait, Tracy, kinetic energy needs velocity. It does, but remember, speed and velocity are measured in the same units, meters per second. Just means I haven't given you a direction. And that doesn't matter because energy is a scalar. So here, if they give us speed or they give us velocity, it doesn't matter, okay? So, we have a mass, 500 grams, but needs to be in kilograms, so that's half a kilogram. That's going at 4 meters per second. So my kinetic energy is a half mass times v squared. So it's a half times 0.5 times 4 squared. We're going to use our calculators. So a half is 0.5 times 0.5 times 4 squared, and it gives me 4. Tiny kinetic energy, but I'm okay with that. It is a small object going at a relatively slow velocity. 4 meters per second isn't that fast. So I'm okay, 4 joules, nice and small. So, next one. A child throws a 150-gram ball with a velocity of 5. That's quite fast. Okay, and we want kinetic energy. Alrighty, so we do the same thing. Mass, 150 grams, 0.15 kilograms. Remember, I divided by 1,000. Velocity is 5. I'm not expecting a big value here because of the small mass. So EK is a half mass times velocity squared. So it's a half times 0.15 times 5 squared. I absolutely need my calculator. So it's a half, so 0.5 times 0.15 times 5 squared. And I get 1,8. Remember, we round off to 2 decimal places, so 1,88. And like I said, when I looked at it, I went, oh, it's going to be a small value. Mainly because the mass was so small. Okay, that was the big deciding factor for me. When you do these calculations, look at the information you're given. Then look at the answer you get and always say to yourself, does my answer make sense? So if I'm getting a big value for a tiny little object, I've probably made a mistake. Okay? So you need to look at it and go, always say to yourself, does my answer make sense? If it does, we're good. If it doesn't, go back and look at what you've done. It's very likely that you didn't convert your mass properly. That's the big mistake. Mass must be in kilograms. Okay? So, keeping that in mind, we're going to take a short break, and I'll see you in a couple of minutes. Welcome back, everyone. I hope you've got lots of energy during your break so we can do some more calculations. So let's just get going, shall we? First question. A box, oopsie, maybe I should have a pen, of 200 kilograms is lifted to a height of 10 meters. And now there's 2 questions. The first one is, calculate the potential energy of the box. We're good with that. If the height of the box is now 20 meters, how does the potential energy of the box change? Well, let's start with the easy one. We have a box of mass 200 kilograms. They tell me that it's a height of 10 meters. They want the potential energy. We've done this lots now, so we can do this. So potential energy is mass times gravity times height. So we have 200 times 9,8 times 10. So we take 200 times 9.8 times 10, 19,600. I'm happy with that value because it's a big mass. Okay, 200 kilograms is heavy. So I expected a big potential energy here, okay? Second part of the question. They now tell you that it's lifted to a height of 20. And they want to know how the potential energy changes. Now, you've got to be careful. They haven't asked you what is the new potential. If they did that, then it's easy. We could just put everything into the equation, get an answer. They asked, how does it change? This is asking you, does the potential energy get bigger or smaller? And how much does it change by? What are they asking you to take into consideration? The fact that potential energy is directly proportional to height. It went from 10 meters to 20 meters. 20 is 2 times 10. So my height doubled. Okay, so height doubled. Because potential and height are directly proportional to each other, if the height doubled, my potential energy doubles. So my answer is this. The potential energy, and we write it out nicely, will double. Now, if you couldn't see that, you are welcome to work it out. But I won't accept that value that you work out as the answer, because you're not telling me how it changed, you're telling me what it changed to. So just be careful. How? Description. If they said, what is the new potential? Answer. Value. Okay. A girl of mass, 55 kilograms, climbs up a flight of stairs to get to her next lesson. She's at school, obviously. Calculate her potential energy at the top of the stairs. So this is a basic diagram of the stairs. They're saying the vertical height is 5.5 meters. Sounds quite high, but we'll go with it. And it's 15 meters at an angle. So when we look at this, we know mass is 55 kilograms. I'll talk about the heights in a second. We want potential. In order to work out potential, I need to know height. I've got two values. I've got a 5.5 and I've got a 15. When I look at potential energy, it's vertical height, perpendicular height. All right, so actually the height that's important is the 5.5. The 15 doesn't matter. It doesn't matter how many stairs she went up. It doesn't matter whether they were winding stairs. It makes no difference. All I'm concerned about is that from where she started to where she ended, that height was 5.5 meters. So here, I put 5.5. The distance, at 15 meters, we're going to consider later on in your curriculum, and we're going to look at what happens to energy because of that. But for now, we're not interested in that. We just want the vertical height. So, potential energy, mass, times gravity, times height, 55 times 9,8 times 5.5. So let's do this. So we've got 55 times 9.8 times 5.5, and we get 2,964.5. So let's write our answer down. Oh, maybe I should have a pen. There we go. 2,000, now I've forgotten the answer, 964.5 joules. Okay, I'm happy with that answer. It was 5.5 meters, not that high, 55 kilograms, not that heavy. I'm good with that answer. Next one. An athlete of mass 65 kilograms runs at a constant speed of 4. On this note, we're only going to be working with constant speeds when it comes to kinetic energy, okay, at this point. Because if the speed's changing, then his kinetic energy is constantly changing. So for now, we're just going to simplify it, all right? They ask for two things. Calculate his kinetic energy originally. Then they say if his speed halves, calculate his new kinetic energy. So let's start with the first one. Mass, 65 kilograms. Speed, 4 meters per second. Kinetic energy is a half mv squared. So it's a half times 65 times 4 squared. We absolutely need our calculators. So 0.5 times 65 times 4 squared, 520. That's okay, it's not a bad one. He wasn't growing that fast, he's not that heavy. I'm okay with that. Now they say his speed halves. And then they want you to calculate his new kinetic energy. This is different than the question we did earlier with the potential, because that question said, how does the potential change? Here, they want you to calculate his new kinetic energy. In other words, they want a value. So, his mass hasn't changed. His speed, though, is now half what it was. Now it's 2 meters per second. What I'm expecting is that his kinetic energy is going to be 4 times smaller. Okay, so let's see if that's right. EK is a half mv squared, so it's a half times 65 times 2 squared. Okay, now that answers the one we had last time, so it was 520. Let's just quickly put that there. I'm going to remind myself of that just now. And now we've got half times 65 times 2 squared, and we get 130. Now, I said to you that I expect that this must be 4 times smaller than my original. Let's see if that is what happened. So I'm going to go 520 divided by 130, and I get 4. You can see it's 4. So I got exactly what I was expecting. The velocity halved, and the kinetic energy became 4 times smaller, because kinetic energy, remember, is directly proportional to v squared. That square is very, 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 very important. Okay, so we've done lots today. Done different ways of us asking the questions. It's about reading, so remembering whether you need to do a calculation or do a explanation type question. As with everything, this is about practice, practice, practice. And we've run out of time. So that's all for today, and I will see you again next time.